All right, so you're working with Kubernetes, right? And let's be honest, sometimes parts of it feel like a bit of a black box, especially, I think, when you get into networking. That's exactly why we're here today for this deep dive. We want to untangle some of those knots, give you those insights that really help make things click. Today, we're going deep on the communication backbone itself, Kubernetes networking. And look, this isn't just for the hardcore network engineers out there. This is like the invisible force that makes all those cool distributed applications actually work together.
Oh, absolutely. It's totally crucial. I mean, understanding how your services and pods talk to each other, that's foundational. It's really what lets you build resilient systems. It definitely simplifies management. And honestly, it's often the key when you're trying to figure out why something isn't working right. Troubleshooting often leads back here.
Okay, so to really get our heads around this, we're focusing on three core bits. CNI, that's the container network interface, then DNS, the domain name system, and finally pod-to-pod networking. And just to sort of set the scene quickly, maybe think of Kubernetes networking like a city's communication system, CNI. Those are the engineers putting in the phone lines, right? Making sure every building, every house gets a connection, gets an address.
Yeah, laying the groundwork.
Exactly.
Yeah.
And DNS, that's the city phone book. Gives everything an easy name so you don't need the super long, complicated number.
Makes finding things much easier.
And pod-to-pod networking is just, well, it's the direct calls between those houses, letting them talk directly no matter where they are in the city, or cluster in our case.
Okay, let's unpack that a bit more then. When we say Kubernetes networking, what we're really talking about is how all the pieces, containers, pods, services communicate inside the cluster and, with the outside world too. And like we just said, it really hangs on those three key things: CNI, DNS, pod to pod. Precisely. So CNI, the Container Network Interface, it's both a specification, a standard, and a plugin system. It dictates how containers and pods actually get connected to the network. So that involves, well, everything from setting up their network interfaces, assigning the IP addresses, handling the routing rules. It's basically the network plumbing for the pods.
The plumbing, right. Makes sense. And DNS.
So DNS, the domain name system, is built right into Kubernetes. Usually it's core DNS these days. Its main job is giving those human-readable names to your pods and, more importantly, your services. So instead of chasing some IP address that might change any second if a pod restarts or moves,
Which they do.
which they absolutely do, you just use a stable name like my cool service,
Yeah.
much more reliable.
Okay. And the third piece, pod-to-pod.
Right. Pod-to-pod networking. This is the magic that lets pods talk directly to each other, even if they're running on completely different machines, different nodes in your cluster. Each pod gets its own unique IP address, and they typically exist in what we call a flat network within the cluster, meaning pod A can just directly send traffic to pod B's IP address. No complex NATing or port mapping between pods needed inside the cluster.
So it's like they all have their own direct line phone number within the city.
Exactly. CNI sets up the lines and gives the number, DNS provides the phone book listing, and pod-to-pod is the ability to just dial direct.
Okay, it makes sense broken down like that. But can you give some concrete examples? Like, where does this actually play out in a real application?
Yeah, sure. Think about a typical web application. You've got a front-end web server pod, right? It probably needs to get data from a back-end database pod. The front-end doesn't or shouldn't care about the database pod's IP address. It just asks for, say, database service. That's DNS working. Then maybe that front end is on node 1 and the database is on node 5. Pod-to-pod networking, enabled by the CNI plugin, makes sure that connection can happen directly across those nodes. Or think about microservices. You might have an order service on one node needing to talk to an inventory service on another node via an API call. That's pod-to-pod again. And the CNI plugin itself, maybe something like Calico or Flannel or Cilium, is actually doing the low-level work, setting up virtual interfaces, managing IP address allocation from a pool, configuring routes, maybe even enforcing network security policies saying who can talk to whom.
Right, the CNI plugin is doing that heavy lifting underneath. Okay, so we see the pieces. But let's talk about the why. I mean, why are these specific components so important? What big problems do they solve compared to, I don't know, older ways of doing things, especially for these distributed apps that are constantly chatting?
That's a great question. I mean, what this whole system really provides is a robust, scalable, and pretty flexible framework that honestly hides a ton of complexity. Think about seamless connectivity first. CNI basically guarantees that your pods get network connectivity in a consistent way, no matter if you're running Kubernetes on AWS or Google Cloud or Azure or even on your own servers, right?
Ah, so it abstracts the underlying network differences?
Exactly. Your application's networking just works the same way conceptually everywhere. That used to be a massive headache, different network setups for different environments. Then simplified addressing with DNS, we touched on this, but using stable names like my-service.default.svc.cluster.local instead of IPs that can change anytime a pod restarts or gets rescheduled, that's huge for reliability in distributed systems. You avoid so many potential connection errors.
Yeah, chasing down IP changes sounds like a nightmare.
It really is. And then direct communication with pod-to-pod networking. Because each pod gets its own IP in that flat network, they can talk directly. This is super efficient. You don't necessarily need complex proxies or load balancers between every single microservice interaction inside the cluster. It cuts down latency.
Okay, efficiency and directness.
And that ties into scalability, too. When your application needs to scale up, Kubernetes just spins up new pods. CNI gives them IPs, DNS makes them discoverable if they're part of a service, and they instantly join the network. It all happens automatically. No manual network config needed for scaling.
Right, imagine having to manually assign IPs every time you scaled up.
Oh, man, yeah. No thanks. And finally, something that's increasingly important, security and control. Many CNI plugins like Calico or Cilium allow you to define network policies. These are like firewall rules, but for your pods. You can say only pods with the label frontend can talk to pods with the label backend on port 8080. That kind of granular control is critical for security in a microservices world.
That sounds really powerful. So flipping it around, what would happen if you didn't have these? It sounds like things would just fall apart.
Pretty much, yeah. Without a CNI plugin installed and configured, your pods simply wouldn't get any network interface or IP address. They'd be completely isolated, unable to talk to anything.
Okay, so CNI is non-negotiable. What about DNS?
Well, without the built-in DNS, pods could technically find each other using IP addresses, but remember, those IPs change. A complex, brittle mechanism to constantly track the current IP of every service it needs to talk to. It would be extremely fragile.
Right, asking for trouble.
Meh.
And without direct, pod to pod.
If pods couldn't talk directly across nodes, you'd probably have to rely on things like node port services or external load balancers for all inter-service communication, even within the cluster. That adds hops, increases latency, and makes the whole setup way more complex and potentially expensive to manage.
Okay, so the combination is really what makes it work smoothly.
Definitely. Let's go back to that e-commerce example. Front-end needs product data from the back-end service. CNI ensures both the front-end pod and the back-end pod get IPs and network interfaces. They're on the network. DNS lets the front-end simply ask for back-end service, and Kubernetes DNS resolves that to the back-end service's stable cluster IP. Then, the underlying pod-to-pod networking, managed by CNI, ensures the actual packets flow directly from the front-end pod to one of the healthy back-end pods, even if they're on different nodes. It all works together seamlessly. That simple data fetch relies on all three.
Okay, that paints a clearer picture of the why. Now let's pull back the curtain a bit more. How do these three actually work together, like mechanically? What's the flow?
Right, the how. It's actually a pretty neat orchestration. So when you tell Kubernetes, hey, create this pod, the kubelet on the assigned node sees this request. One of the first things it does is called a configured CNI plugin. Let's say you're using Calico. The Calico CNI plugin gets invoked. It then does a few things.
Right.
It assigns a unique IP address to the pod from its configured IP pool, maybe 10.244.115. It creates a network interface, like Eth004, inside the pod's network namespace. And crucially, it sets up the necessary routes or network connections on the node so this pod can reach other pods, potentially using things like BGP routing or an overlay network like VXLAN, depending on the CNI.
So CNI does the actual setup for each pod as it starts.
It gets it onto the network. Now, in parallel, or maybe slightly after, the Kubernetes DNS system, usually CoreDNS, gets involved. CoreDNS is constantly watching the Kubernetes API. When a service is created or updated, or even sometimes for pods themselves, CoreDNS creates the necessary DNS records. So when your front-end pod makes a DNS query for db-service.default.svc.cluster.local, that query goes to CoreDNS running inside the cluster. CoreDNS looks it up and says, that resolves to the cluster IP 10.96.0.10 and sends that back to the front-end pod.
Okay, so CoreDNS is like the internal phone book operator.
Precisely. And then for the actual pod-to-pod communication, Once the front-end pod knows the target IP, either another pod's direct IP or a services cluster IP, which then gets routed to a pod, it just sends the packet. Because of the flat network created by the CNI plugin, the packet can typically be routed directly from the source pod's IP, ING 10.244.1.5 on node 1, to the destination pod's IP, ING 10.244.2.7 on node 2. The underlying CNI magic handles getting the packet across the node boundary.
So the CNI lays the tracks, DNS provides the address, and the packet just travels directly on those tracks.
That's a good way to put it. And services are key here too. A service provides that stable cluster IP, 10.96.0.0 in our example, and DNS name, DB service. When your front end sends traffic to that cluster IP, Kubernetes networking components like kube-proxy or perhaps eBPF rules set up by the CNI intercept that traffic. They then load balance it to one of the healthy pods backing that service, like 10.244.2.7. So the front end talks to the stable service IP, but the actual connection happens via pod-to-pod networking to one of the backend pods. It abstracts away the individual pod IPs changing.
That abstraction seems really vital. You mentioned network policies earlier, too. How do they fit into this flow?
Right, network policies. These are implemented by the CNI plugin, assuming it supports them, like Calico, Cilium, or WeaveNet do. When you apply a network policy object in Kubernetes, the CNI plugin translates those rules into actual firewall rules like iptables or eBPF or other mechanisms on the nodes. So before a packet from pod A can reach pod B, it's checked against these rules. If a policy says pods labeled front end can talk to pods labeled back end on port 5432, and pod A is a front end and pod B is a back end, the packet flows. If pod A tries to talk to a payment pod and there's no rule allowing it, the CNI's enforcement mechanism will drop the packet.
Ah, so it's like security guards checking IDs at specific checkpoints along those communication lines set up by CNI.
Exactly. It adds that layer of security enforcement directly into the network fabric managed by CNI. And like you hinted at before, this can be amazing for troubleshooting too. If service A suddenly can't talk to service B, checking the network policies is often a good first step. Maybe a policy is too restrictive or missing.
Yeah, I can see that. Okay, so if we were to boil it down, the really key things for listeners to remember from this how part seem to be the CNI plugin, doing the pod network setup, core DNS, handling the name lookups, the cluster IP, that stable address for services, and this idea of a flat network, allowing direct pod communication.
Absolutely. Those are the core building blocks that work together.
Okay, so let's try and bring this all home then. If we go back to our city analogy one last time, Kubernetes networking is like that super well-organized communication system for your whole cluster, your whole application city. CNI is laying down all the phone lines, giving every single pod its own unique phone number, its IP address, and making sure the lines connect properly.
Yep, the infrastructure layer.
DNS is the essential city phone book, the directory service. It lets pods find each other using simple, memorable names instead of those long IP numbers.
Makes discovery easy and reliable.
And pod-to-pod networking is just the system working, ensuring that any pod can make a direct call, send a direct message to any other pod, no matter which part of the city, which node they happen to be in.
That seamless direct communication. That's right. And honestly, getting a handle on these foundational bits, CNI, DNS, pod to pod, it really is key. It helps you feel much more confident working with Kubernetes, whatever your role is. It's about understanding how your applications actually talk to each other when they're running distributed like this. It moves you beyond just thinking about deploying containers to understanding the system.
Definitely. So maybe a final thought for everyone listening to chew on. Now that you have hopefully a clearer picture of how pods and services connect and communicate using CNI, DNS, and pod-to-pod networking, what new ideas does that spark? How might this understanding help you design applications that are even more resilient or scalable? And maybe just as importantly, when things do inevitably go wrong, how might knowing about these layers help you track down the problem faster when services aren't talking like they should? Something to think about.